My name is Elizabeth Barnes, and I'm a professor at Colorado State University. And today I'm going to talk to you about work we are doing using neural networks to view forced climate patterns. First, I want to thank all of the wonderful people that have been working with me on this project. And I want to specifically point out my graduate student, Ben Toms, who is in attendance today and is there for discussions after the session since I unfortunately cannot be there with you today. So climate change in the 21st century is really a signal to noise problem. So what I'm showing you here is a picture of the surface temperature change between the end of the 21st century and the beginning of the 20th century. Now, these temperature changes have been averaged over 29 different climate models and are under the RCP 8.5 future climate scenario. So a scenario with quite a bit of anthropogenic emissions. Now, the first thing we see from this plot is red everywhere. And that's just telling us that the globe is warming with climate change, something we all know. In addition, we see that the Arctic is much redder than the rest of the globe. And this is known as Arctic amplification, the idea that the Arctic warms faster than everywhere else. Now, while this picture of climate change is well known to many of us, what's hidden under this picture are really two sources of uncertainty. The first is the idea of structural model uncertainty or model disagreement. The idea that we have 29 different climate models here that all have slightly different ways of simulating the Earth system and its response to climate change. And all of that is hidden within this average. In addition, we have another source of uncertainty, which is the idea of internal variability or climate noise. Even if we had nearly perfect models and a nearly perfect understanding about how the future would evolve, we would still have uncertainty from the fact that the climate system is a noisy, chaotic system, and that tiny little perturbations or tiny little errors could lead to huge errors in projections. This is often known as the butterfly effect, if you are familiar with that concept. Now, these two sources of uncertainty make things really difficult for us because on Earth, we really only have one world, and that one world shows particular trends. For example, here are observed present-day trends in temperature. And the big question we're always asking is how can we tell which trends or changes are signal and which are the noise in this one observed Earth? So I'm going to show you how we are approaching this today with neural networks. Specifically, what we're going to do is we are going to train a neural network to predict the year of a map. And here's a picture showing that more clearly. What we're going to do is we are going to take an annual mean map of surface temperature, like the one shown on the left, input it into our neural network, and we are going to task the neural network with predicting the year from which that map came. So if I input a map from 2018, then it's going to hopefully predict the year 2018. And for those of you familiar with neural networks, we use a rather shallow network with only 2 hidden layers of 10 units each. So before I show you our big results, I'm first going to test on something we know won't work. Specifically, we're going to take a control simulation with constant 1850 forcing. So this is a climate model. In this particular model simulation, variations from one year to the next are only due to internal climate variability or climate noise. And for that reason, there are no reliable indicators of the year for the neural network to learn from. Thus, the neural network performs very poorly. This is seen here where the x-axis is the actual year of the map that I gave the neural network, and the y-axis is the predicted year by the neural network. The gray dots are the training data, the data that the neural network was trained on, and it does a very good job with those years, as shown by the one-to-one line, except this is really overfitting, because when we give the neural network maps it's never seen before, shown in black, it does a very poor job at predicting the year because there's no information there. So the whole idea here is that the neural network must learn regional signals that are reliable indicators of the year. And those regional signals are going to be from the forced response to climate change. So here's how it works when we actually input these climate model simulations with anthropogenic emissions included. Again, the x-axis is the actual year and the y-axis is the year predicted by the neural network. Now the gray dots, which you can't see, is the training data, and that's because the neural network does such a good job that those data fall relatively on the one-to-one line. The color dots are results from climate models that the neural network was not trained on, known as the testing data. And what you can see is that after about 1960, the neural network does a very good job at predicting the year of each of the maps. Now, prior to 1960, the neural network fails to do a good job, and this actually makes physical sense. What this is telling us is that the forced response to climate change is so weak, or the CO2, which is the largest climate signal in these runs, is so weak that there's really nothing to learn from. It's not until after about 1960 that the neural network is able to pick up on forced patterns of change. Now, the neat thing with our setup here is the real world also has maps of temperature, and we can input these maps into our neural network and see how it does. Does it know what year that these maps came from? And that's now shown as these white dots. What surprised us is that the neural network does a very good job at predicting the year from observed temperature maps. This implies that the patterns that it's picking up in the climate models are also present in the observations. Now, surface temperature exhibits one of the most robust responses to climate change, so you may not be all that impressed that I've just found patterns of climate change in surface temperature maps. However, precipitation is very noisy and has large disagreement across climate models. So the question is, how does this method perform when we feed the neural network maps of precipitation and ask it to predict the year? And that's shown here. So even though precipitation is so noisy, the neural network can still identify the year from maps of precipitation in both models, shown in the colored dots, and observations, which is shown in the white dots. Again, the one-to-one line means a perfect prediction. So thus far, I've really only shown you that I can train a neural network to take maps and predict the year. But the real question, the real science question here, is what patterns allowed the neural network to identify the year in the first place? Predicting the year in and of itself is actually quite boring. We all know it's 2019. What we'd rather know is what made the neural network know in looking at one of these annual mean maps that it was 2019. The whole idea of neural network visualization is a really exciting field right now in computer science. And the idea is just something like an X-ray machine at an airport. You put a black backpack, or a black box neural network in our case, through these tools, and you get an inside view of what's going on inside this particular black system. So it's not so black anymore. Now, just like an X-ray machine, it's not a perfect inside view, but it's better than nothing. The method we're going to use is called layer-wise relevance propagation, and this is a new one of the many new tools coming out in computer science. And the idea is quite simple. It takes the output of the neural network, this denoted as f of x in the top figure, and then it propagates that output or that prediction backwards through the neural network to try and understand what parts of the input led to that particular prediction. An example here is shown on the right, where a neural network was trained to identify handwritten numerals. And in this case, this LRP method, layer-wise relevance propagation method, outputs a heat map showing which parts of the image it used to know what the number was. So if you look at the number 2, it identifies the fact that it used the handwritten areas to identify the 2. The neat thing is we can apply this to our problem. Specifically, when the neural network makes a prediction of the year, we can use these tools to ask the question, which regions of the globe were relevant for correctly predicting that particular year? And we can make a map that looks like this. So this is a composite map for when the neural network predicts the year 2025 correctly. And these green locations show the relevant regions that were important or relevant for the neural network to make an accurate prediction. And what we see here is that really it's the Southern Ocean and the North Atlantic, as well as Southern Asia, that were used by the neural network to know that the year was 2025 and not some other year. We can do this for many different decades and see how these learned indicator patterns of force change throughout the 20th and 21st century. For example, in the 90s and early 2000s, it's the Southern Ocean and the North Atlantic that are really the most reliable indicators of change. While by the end of the 21st century, in 2095, it's the Indian Ocean and the North Pacific that jump out as being the most important and relevant for the neural network. Now, these indicator patterns of forced change are really made up of three pieces. First, regions where the climate change signal is large. Second, where internal variability is small, so the signal emerges. And third, locations where the 29 climate models agreed on the response. That is, regions where the models disagreed, the neural network learned to ignore. Now, if you recall, the forced response to climate change looks like this, with the largest warming being over the Arctic. However, the neural network does not rely on the Arctic to make its predictions. And that's because while the Arctic has a very large signal, it has very large noise as well, and climate models often disagree on the magnitude of the change. So the neural network learns to find other regions of the globe that are more reliable indicators. Finally, to wrap this up, a neat thing we can now do is we can take the neural network predictions from observation, so what's actually happened on Earth. So for example, here is a map of temperature anomalies that were observed in 2000, and we can ask the network, where did it look when it made its prediction from this observed map? And the relevant regions used by the network are once again the Southern Ocean, as well as the coast of South America, as well as other regions. And what's interesting is if you look at the observed temperature anomalies on the left, they aren't terribly large in these regions. What it says is that the neural network is not necessarily focusing on the largest anomalies, but the regions that are most reliable indicators of change. So in my mind, neural networks for climate science are a very exciting new avenue of research. Here I've shown you that artificial neural networks can identify forced climate patterns amidst the noise as early as the 1960s. And this work has just been published a few weeks ago in Geophysical Research Letters, if you're interested. Second, neural networks are no longer black boxes. Tools exist now to help visualize their decisions. And this, in my mind, is an absolute game changer for neural network applications in geoscience. And my graduate student, Ben Toms, who is here today, has recently written a paper introducing these visualization methods to the geoscience community, and a preprint is available on arXiv. Putting these two together, in my mind, if you take nothing away from this talk, it's that neural networks can be used for more than just prediction. In my example, predicting the year is actually quite boring. What's interesting is how the network came to that prediction, or what information it used. That is, the science can be what the network learned rather than the prediction itself. And this opens up a huge avenue of research and allows us as scientists to really get creative. So thank you for your time, and that concludes my talk. Thank you.